Here's explanations for the damping and resonance homework. Question number 3. This is a method for weighing small objects using a carbon nanotube. SHM, particularly mass spring systems, are a way of measuring mass in different situations. It's how astronauts measure their mass in orbit. And obviously if they stood on some scales, the scales will read 0, so they sit in a sort of frame and oscillate backwards and forwards. But this is vibrating a carbon particle on a nanotube. What is the name given to the sense of vibration? One such experiment vibrates with a maximum amplitude when at a frequency of 970 kilohertz. What is the name given to the frequency at which an object vibrates with maximum amplitude? That is the natural frequency. So a pendulum, a mass spring system, everything has a natural frequency, which if it's displaced, it oscillates with that. To work it out, you use the equation. Here, so this is a mass modelled as a mass on a spring. Calculate the mass of the carbon particle. So mass on a spring, 2t equals 2 pi root m over k. And we want to work out what m is. So first of all, I'm going to square everything. And we want to work out what m is, so we're going to take t squared k divided by 4 pi squared equals m. I hope you're all showing your working in your answers. So I'm just going to rearrange this again because what we've got here is we've got the time period here, so the time period is 1 over f squared k over 4 pi squared. So m equals k over 4 pi squared f squared. So k is 0.81 divided by 4 pi squared f squared, and f is 970 times 10 to the 3 because it's kilohertz squared divided by 4 pi squared. 2.2 times 10 to the minus 14 kilograms. What assumptions have been made? Well, we've assumed that this is a simple harmonic oscillator, our mass on a spring, so we need to think about how that would affect the frequency. So we can say that it's not past the elastic limit. We're saying that we're using this equation. We can only use this equation when it's lightly damped. If it's heavily damped, the time period will change, so we can say that there are minimal resistive forces, and this part of the nanotube here, well, given this part here at the end, given the scale of the diagram, we're kind of led to believe that this nanotube is sort of the same order of size as the vibrating carbon particle. So we're kind of assuming that this doesn't have any mass. The centre of mass of this system, will look at the diagram, will probably be somewhere along there. But we're ignoring the mass of the nanotube and assuming all the mass is at the ends there.